Thanks, everybody. It's really a delight to be back here in Berlin. I love it here. And I'm happy to talk about HTTP routing in Go. Routing, routing, routes, routes, I don't know. It's English. So what we did was we added some things to the standard ServeMux routing patterns. And that's the topic of the talk. And you can use that right now. Not right now. Wait till my talk's done. But yeah, it's in Go 122 out since February. So I'll talk about those new features. That'll actually take very little time. And then I'll talk about precedence and conflicts. I'll explain what that is. And then performance. So what is, I'm going to call it routing. Routing, what is routing? It's this, whatever takes you from an HTTP request to the actual code that satisfies that request. Whatever's in that purple cloud is routing. And typically this is done with some sort of pattern that matches the request. That's how most people do it. Of course, you can always just write code to do it, which is why I call it a game. Because you can always just write code to do whatever you want, and we'll see examples of that. But it's nice to have some sort of pattern that helps you avoid writing a lot of code. And what kind of patterns can you have? It could be a literal path, maybe something with a wildcard, maybe a wildcard that matches everything to the end of the path. Maybe the wildcard has types in it so that the thing only matches, the pattern only matches if it's the right type. Maybe you allow regular expressions. You can get arbitrarily complicated. And as I said, you could just write code to do that. For example, if your routing pattern language doesn't talk about methods, you can just ask for the method in the code, check the method in the code. So that's why it's a game. And I recommend that you don't try to win this game, because you'll just get something that's very complex, and it's not always going to be useful to a lot of people. So as you know, this is Go, so we favor simplicity. In other words, chill. So let me talk about what we put in. But first, what do we have now? What did we have in 121? And we still have it for backwards compatibility. You could use a literal path, or you could use a path that ends in a slash, and that means that anything with that prefix would match. And we added just a few things to that, 4 things. Methods, a couple of kinds of wildcards, and a $ thing, and I'll talk about each one of those. Methods. You can say in the string which HTTP method must match this pattern. And it must match it exactly, except that for get we also include head, because the spec says head request is exactly a get request, but you just discard the body. And Go is actually already, the Go HTTP package already did that. So we just are following that. The spec also says if you would have matched except you gave the wrong method, but the rest of the path matches, then don't return a 404, return a 405. And tell the person, the endpoint, the client, what methods they could have used to get it right. So we do that too. Wildcards. A wildcard is anything in curly braces. It must be a complete segment. There's no types or regex involved. And you can use ... for the last wildcard to mean match everything else in the path, in the URL path. And the sort of weird $ thing sort of fixes an issue with the original design, which we couldn't fix directly, which is that let's say you actually want to match a path that ends in a slash. In the original design, that really means match anything with that prefix. So if you really literally want to match that path, you can write this curly brace $ thing, reminiscent of the regular expression $, meaning end here. And lastly, you need to be able to get those wildcard values, so we added a method to the HTTP request type called path value. There's already a form value, now we have path value, and that pulls out the value of the wildcards that you match to get to this piece of code. And that's it. So what are we going to do for the next 25 minutes? I'm going to talk about, first of all, precedence and conflicts. So precedence means when you have two patterns matching the same request, which one do you pick? Which takes precedence? And some routing packages are like, well, you can't have two patterns matching the same request. That's one answer. You just can't do it. Others take the first one you register or the last one you register. But what Go has always done is we use these two simple rules. First of all, I hadn't mentioned this, but you can specify the host in the it's not commonly used, I think, but you can specify the host in the pattern. And that a pattern with a host always takes precedence over one without. And otherwise, its longest wins. This is the existing rule. The 121 rule. Longest pattern wins. And you'll only get a conflict if you register the same pattern twice. And in that case, the ServeMux.handle method will panic. And the nice thing about this is that the registration order doesn't matter at all. Doesn't matter which order you register your patterns in, you'll have the same effect. You may get a panic if you have a conflict, but if you don't, you can switch around your code, refactor it however you want, and you'll get the same result. That's a really nice property that we want to maintain, and we have to maintain for backwards compatibility. So let's try the same idea with the new language features, the new pattern features. Host takes precedence over no host. For methods, it would sort of make sense if you've gone to the trouble of writing a method, that should take precedence over a pattern that doesn't specify a method. So if you had these two patterns here, you're saying any get with /page will be handled with one piece of code, and any other method that you pass would be handled by a different piece of code. And then for the paths, how about longest path wins? How's that going to work out for us? Not so great, because that would depend on the variable names you chose. And the precedence should not depend on the length of the variable names that you chose. That seems wrong. All right, so how about we'll just treat all wildcards as length 1. Well, now we have a bunch of problems here. Let's just look at the last one. I think that's the easiest one to understand. These patterns would have the same length, right? So there'd be no precedence order. Neither one would win. But it's my intuition, and I hope it's yours, that letter/x should take precedence over letters/wildcard. And in the other two cases, if you look at them, you may also feel, as I do, that the left-hand one should take precedence. But they would be equal according to this longest path with wildcard length being length 1. That doesn't work. It was suggested to use the longest literal prefix. So that would make letter/x win, because the literal part, the non-wildcard part, is longer than the non-wildcard part of the other one. But then you get things like this. You have a root that says, for any user, I want to look at the last post they made, or I want to just look at any post by ID. And again, it seems like the first one should win. And if that is your intuition, I will make that precise, I hope, in a few slides. But the longest literal prefix here is the same, /user/. So longest literal prefix doesn't really seem to capture what we, or at least I intuitively felt, was the precedence order. So let's all take a deep breath. As I did, I spent a day or so lying on my back in a room in the dark, not literally, but I actually used to do that when I had a math problem. But I thought a lot about what's really going on here, and because I tried a lot of other syntactic rules, and they just got more and more complicated and convoluted, and there was always cases that caused a problem. So let's go back to basics. What do we mean when we have a bunch of roots, and we have one at the bottom that says basically just /, meaning match anything? Well, I mean, that's what we mean. We mean this last one is supposed to match everything else. We have a bunch of stuff, and then we have just something that's like, I'm going to 404 with this, or I'm going to do some sort of special handling. So if you think about it that way, then you sort of maybe think about this picture, a Venn diagram, where what these sets are the sets of requests that you match. So /path ... or just plain / matches everything. And then these other more specific paths match subsets. of the space of possible requests, the infinite space of possible requests. So if you think about it that way, the rule is pretty obvious, I think. Subsets take precedence. If you have two patterns and one matches a subset of the requests of the other, the one that matches the subset takes precedence. And that seems to, at least for me, that sort of satisfies my intuition about all the patterns that we've seen so far. They're always more specific. They match the subset. What if two patterns overlap? So this is an actual example I found on the internet, because I looked at a lot of these things. So is export/events, is exports a domain with events, or is events the ID of an export? I don't know. You don't know. Nobody knows. So certainly we can't expect ServeMux to know. Well, somebody knows, whoever wrote these. But we couldn't expect the code to disambiguate. So this has to be a conflict. So the rule is one pattern takes precedence over another if it matches a strict subset of requests. Otherwise, they conflict if they overlap at all. And we need one asterisk there for the hosts because for backwards compatibility. That technically breaks this rule. But you can usually ignore that. So we now have one really simple rule to state that gives us an intuitive sense of precedence. And just to review, so here are the 5 relationships between two patterns. They can be totally disjoint, in which case there's no problem. You'll never have a request that matches both. One or the other can be more general or more specific. They can overlap, or they can be identical, which is just they totally overlap. And both of those cases conflict. I should say not identical. They may not be syntactically the same string, but they both match the exact same set of patterns. And if you have a conflict, it's not the end of the world. You can always write code. So let's say you think that exports/events exports is a domain of events. You write that as the more specific pattern, and then you write a more general pattern that just matches any 2-element path. And then in code, you can do any checks you want to make sure that that first element is actually the word exports. Or you can switch on other values for that first element. So you can always get around the conflicts in code. So let me take a little tangent here and talk about regular expressions in regular languages. So one of my favorite classes I ever took was theory of computation, like one of the first classes I took in computer science in college. I loved it because it was really abstract. You didn't have to touch anything. And that's where I first learned about regular expressions. As a mathematical theory, rather than as we know them all as a very useful tool for pulling out pieces of text. But before they were ever used for that, 10 years or 20 years before that, they were invented as a purely mathematical formalism. And as mathematicians do, they talk about syntax of things, like A, B star C, the regular expression, and then the semantics, the regular language, or the set of strings that regular expression matches or generates. So I think it was remembering that theory that led me to the idea of thinking about the precedence problem as a semantic problem, not a syntactic problem. It was very frustrating to look at the syntax of these patterns and try to come up with the precedence rule. But as soon as you switch to semantics, it becomes really clear. And indeed, these patterns are a subset of regular expressions. You can write the pattern at the top as, in the usual notation that we all use today, as the regular expression at the bottom. So there's a deep connection there. Now, there's just two problems. Really, there's one big problem when you're talking about a rule based on infinite sets of things, which is how do you compute that rule? So in this case, it breaks into two pieces. Given two patterns, how can we efficiently detect that they conflict? And then, since we're registering a whole bunch of patterns, for each pattern we register, we have to look at all the others to see if they conflict with this one that we're registering. So there's also a second problem there, even if we solve the first efficiently. And it's not really obvious that we can do this, because for general regular expressions, It's decidable to tell that you can write a computer program that will always answer correctly, whether one regular expression matches a subset of the other, but the algorithms are not practical. They're not linear time. So that brings us to the question of performance. And before I answer those two questions, I want to talk about the more general and maybe more obvious question about performance, because those two questions are about when you register something, which is typically at startup time. But what about the more important question of the time it takes when you match something at actual serving time? That's a more sensitive, more time-sensitive issue. Or is it? Or is it? How fast does routing actually have to be? Well, if you read the package doc and the readmes of some popular Go routing packages, you'd think it's pretty important because they say they're optimized for high performance and extreme performance, and they're fast and so on. But, dude, you're using HTTP, a text protocol. You're probably sending JSON, more text. You're doing it over TCP. Okay, maybe that's a good idea. You probably talk to a database over a network. You probably talk to other things over a network. And then you assemble a big old JSON response and you send it over the network. Routing time is not your problem. It is not your problem. If it is, you should be using a binary protocol. You know, you should avoid any sort of routing software. Just get the payload, you know, look at the first byte and dispatch. That's what you do if routing is a problem. You don't use this stuff. So in other words, chill. And you guys are chill because, as we saw, people use GorillaMux. Actually, that's the most popular, despite the show of hands today. That's certainly the most popular third-party routing, and it's 30 times slower than the built-in one. So people correctly do not care about routing performance. Also, I asked on the discussion or the issue, I don't remember which, please, please tell me if routing is your problem, and no one answered. But nevertheless, we did make sure that the new implementation was about as fast as the old. We didn't want to cause a performance regression in case someone did care. Generally, good advice not to do a performance regression. And that was a little bit challenging because the first one just did a couple of Go map lookups, but we managed to achieve something that was approximately as fast. All right, so let's get back to our two performance problems. How do we detect conflicts in two patterns, and then how do we do this for all the patterns you've registered? Well, we can do it in linear time. If you have two patterns, we can walk through them step by step and ask a couple of simple questions and get the answer. So as you walk through, well, obviously, if they're both literals and they're different, they're disjoint. There's nothing more to do. So let's say they're the same literal. Now let's say one of them is a wildcard and the other's not. Well, the wildcard one is more general, right there. Or if they're both wildcards, then they're sort of the same. And if you always find a wildcard, like here, the second one has a wildcard wherever the first does and more, then it's the more general pattern, the other is more specific. You have a subset relationship, and that's fine. But if you ever have a case like in the second pair, where one has a wildcard where the other doesn't and vice versa, that's a conflict. And, super nice, we can construct the conflicting string, or a conflicting string, along the way, right? The conflicting string is the literals that go along with each wildcard. Export/events. So what we do when you have a conflict, we panic, and then we say, you have the code on this line, the registration on this line conflicts with the one on this line, and here's a particular string that causes the conflict. And the ... is a little trickier because basically what you have to say is that the stuff to the left is more general, and then the ... is more general than anything below it. And if both of those things are true, then it's more general. But if you get if you get a kind of a mismatch, then it's going to be a conflict. So that was pairs. Now we have the problem that you're registering n patterns. Each pattern has to check all the existing ones. That's going to be n squared, order n squared. And that we don't want any order n squared algorithms in the standard library if we can avoid it. So what do we do about that? we build an index, is what we did. As far as I know, there's actually no worst case algorithm that's better than n squared for this problem. So in the worst case, we still have an n squared algorithm, which I'll talk about in a second. But the index really helps with every normal case, because if you look at, go ahead, look at it anywhere on the internet, anyone's routing scheme, your own routing scheme, first of all, you're not going to have that many of these, but also it's very likely that you'll have two routes with this, in the same position, two different literal symbols, right? So, you know, users' posts and users' pictures. Right away, these two things are disjoint immediately. There's nothing more to do. And we don't even look, when you register the posts one, we don't even look at the pictures one, or vice versa, because order doesn't matter. Because the index gives us only the things that have the same literals in the same position. So as you register something, we index each position with the literal, and then when we have a new one, we look up, we actually just take the smallest set of any of those matches in the index, and we just compare against that set. So it's fast. Honestly, it was fast even without this on normal sets, but now it's really pretty fast. Can you still construct a set of patterns with n-squared behavior? Yes, you can. Is that likely to happen naturally? No, not likely. So what we're talking about is the kind of worst case situation that security people worry about, where your own worst enemy is constructing some set of roots that is going to mess you up, right? And who is that adversary? It's you, isn't it? You're writing the roots for your server, I hope. I hope you don't have a server that takes roots as requests over the internet and generates another server from that would not be good, for many reasons. So since you're writing your own patterns and you don't want to screw yourself, this is really a non-problem. Last point. As I hope I was clear, and as you know from everything we do and say, we are very concerned with backwards compatibility. So essentially everything I told you today is completely backwards compatible. All the old patterns will work, asterisk, all, and you know, all the other stuff will work. But if you happen to register a pattern that had curly braces before, I don't know why you do that, but if you did, they will now have a different interpretation. So we couldn't maintain backwards compatibility there. We also fixed a long-standing bug that's too boring to talk about, having to do with escapes in URLs along the way. And that technically breaks backwards compatibility. But if you want the old behavior, you can set one of these go debug flags. You should read about these go debug things if you don't know about them. They're a way whenever we have to make breaking changes to get back to the old behavior. So effectively a time machine, as Matt was talking about yesterday. And there's one for this stuff that will give you the old behavior. In fact, it will give you the old code. The old code is just sitting there behind that flag. We don't expect many people will need to do that. So we aim for 80% coverage of features. In other words, as always in the standard library, we want to make 80% of the people satisfied with what we have, and in the interest of keeping things simple, and not try to reach and make things more complex for the 20%. Of course, those numbers are made up. It's not a literal number. But the idea is we satisfy most use cases. So we felt when we looked at the world that the wildcards we chose and the methods would take care of about 80%. So we think that a lot of people can either drop a dependency or just not start with a dependency when they're writing new servers. But you know, if you like what you're using, don't change it. If you need those extra features, you enjoy those extra features, stay with them. And the second and last, the biggest point is that simplicity engenders simplicity. What do I mean by that? We picked a really simple wildcard system. There's no regexps in the wildcard or types. And that enabled us to pick a really simple precedence rule. If the wildcards, for example, could contain regular expressions, we'd be faced with the general problem of regular expression set inclusion, which, as I mentioned, is an intractable. I mean, it's doable, but it would not be practical. So by picking effectively a subset of regular expressions, we were able to efficiently implement that precedence rule. If you're interested in more, these are links to the original discussion, the proposal issue, the documentation, which of course is on pkg.go.dev. It's just added to the documentation for ServeMux. and the blog post that I wrote about this back in February or March. Thank you very much.